We now are moving to the next presentation from Prometheus. Prometheus is a researcher at the iTEAM Research Institute in the Politècnica University of València in Spain, and he will speak about a project on enabling the development of field programmable photonic gated arrays. So we should be able to give you the floor, Prometheus.
All right. Perfect. Am I audible? Hello?
Yes.
Yeah. Can you please confirm that I'm audible? Right. Let's start off. So depending on where you are in the world, a very good morning or a good afternoon to you. My name is Prometheus. I'm from the Universitat Politècnica de València, and I'm also founder of iTEAM Programmable Photonic. And here I'm going to talk about few programmable gate arrays on a generic level about programmable. So to start off with, motivate the need for programmable photonics that we have done ourselves and the work that we are planning, and to conclude. Right. So we started working with programmable photonics somewhere around 2015 with this whole idea of the field programmable photonic gated array, which is the and one thing we found quite interesting when we started off was that there were several concepts which were already using the idea of a generic platform to suffice multiple needs. So one of them, for example, if you're X program, they have done an analysis if you make a which is reusable, so a reusable rocket in that sense, then you actually gain a lot economy of scales that come across. And this in life in general, we have in electronics with move from ASICs to FPGAs, in networks where you have software-defined networks, and in radios as well where you have defined So what do we really need from moving to programming circuits? In photonics, field by design or how the progress, we have already seen that we mirror a lot the developments in electronics. So what we always like to do is start off with what electronics has seen, take it as a motivation, learn the lessons from there, and move forward and try to do the concepts in photonics thereafter. So FPGAs are right now a very common and popular concept in electronics, and moving from ASICs to FPGAs, what we see that it occupies around 50% of the market. The way this trend developed in electronics overall is whereby in 1940s, 1950s, you had these discrete devices coming up, which we have seen in photonics as well. Then you moved on to more ICs, more complex circuitries, then application-specific ICs, and microprocessors, whereby around 1980s we came up with we realized the concept of FPGAs, and now you have this sharing of the market between FPGAs and ASICs. And the main reason for this can be divided into two things. It comes down to cost, but cost in two different levels. So one is the time in itself, because I'll just try to get the pointer up. Yeah. So which is the time to market. Time for companies also translates into cost in some other ways. So that's something which is very useful. So having a generic platform which you can replicate in multiple units and provide to multiple users always helps out, because then the time to market is very low. And you share the non-recurring expenses. So that also implies that especially for medium scale implementations, you distribute this non-recurring expenses in multiple users, whereby your costs come down quite a bit. There are other advantages as well, but these two are the primary drivers and the primary motivations for moving to programmable circuits or programmable, or the idea of programmability in general. What we propose over here, and our whole idea of moving to programmable photonics, does not only encapsulate working on photonics, but also integrating electronics in there. So it's basically a harmony between electronics and photonics, whereby you utilize the best of both worlds and try to provide better functionalities and improvements in the technology in itself. In regards to the fabrication and the non-recurring expenses that I was talking about, and the timeline associated as well, I guess most of you are familiar with the fabrication flow, whereby you start with an idea, you have the fabrication, etc., coming off. And our goal in this case is to have it distributed across multiple users with the use of a generic hardware platform, whereby we bring down both the cost and the timeline associated with it. So you start off with the fabrication of this generic platform, leading on to encapsulation and the assembly, which would start off with the packaging of the chip, and then encapsulation of the assembly with any drivers, etc., that is required, leading on to a section which is a closed encapsulated subsystem, which you can see in this figure over here. You, of course, in every stage have to do the verification as well, whereby you have the complete hardware, which you, after further verification, can send to the end users. And another thing which is important in this case, of course, other than the hardware in itself, is the programmability which is provided by the software. So this added value through the software is something which we are concentrating on a lot as well, because it's a combination of both the hardware that we provide and the software solution, which is, in fact, the enabler to use the hardware. Right. So moving towards the FPGA idea, as I'd mentioned before, we started working on this around 2015. So in photonics in general, the way the trends moved, we had reconfigurable aspects coming across in various formats. So you had circuitries, relatively simplistic ones starting off with, and then you added multifunctionality to this, or a few functionality at first. We moved on to multiple interferometers and circuits, and then around 2015, we started working on this hexagonal mesh idea, which is the basis and the core of the product that we do have, or that we are developing. And then we decided on adding a few things as well, whereby you have things like high-performance building blocks to support the core, and you have your inputs and outputs that are required as well. I'll come back to the core in itself and the high-performance building blocks in one of the later slides. So again, drawing a parallel from electronics, what you generally see over here is that if you shift the progress of electronics by around 30 years or so, which marks around 1960s, the advent of photonics in general, or integrated photonics, this is where we started off with standalone devices, with discrete devices, etc., moving on to more simplistic structures, more complex architectures and circuits, into the aspect eras, which still is very common in photonics. And then around the 2015 mark, we came up with the FPGA idea, and that's what we're trying to commercialize and make into a complete viable product. Now, the basic ideas and the concepts behind it, as I had alluded to before, there are multiple sides of this. So one, we divide this into different tiers. So one, which you see over here, this is the photonics in itself, the photonic chip, which consists of the core, which is the hexagonal mesh. We have high-performance building blocks. Again, this is a similar concept to what you have seen in electronics, that you can have a product with a very specific programmable core, but for certain end users with certain requirements, you can add high-performance building blocks, which can be modulators, which can be high-Q filters, etc., along with the core to facilitate functionality in order to ensure that you do not lose any functionality because of the programmability aspect. So this forms then the entire photonic circuitry, which then would be packaged and would fit onto a platform like this. The rest of the platform, other than the photonics part, is the electronics, which includes the drivers, the readout system, any sort of processing that you want to do here. So to form anything required and dealing with controlling the circuit and to form a full closed feedback loop, which is the electronics style. And to govern all of this, to drive all of this, we have the software tier. This software tier, we want to make it as flexible as possible. So for example, someone coming from networks can use it directly, the hardware, as a black box and program or basically achieve a certain functionality as they desire. If the end user wants to do their own configurations, they can as well, although we do provide our self-configuration algorithms, and this is all driven by a backend API. In the end, then, going into details of every tier that we have, what we propose is a solution which would look like this, where you can again see the hexagonal mesh, which is the core coming across. These smaller blocks on the side are the high-performance building blocks. And you have the fiber array as well, connecting onto the photonic integrated circuit, providing the optical IOs. You have drivers across and readout systems as well. So this, for example, can be a laser, which then comes back into the photonic chip if you want to keep it outside of the chip. But as we have seen from the previous speaker, there are possibilities of incorporating the laser in the system as well, in the photonic part of the system. And then you would drive all of this and control and manage the whole system using a software system which looks like this. So this would be a GUI, whereby, again, similar to what I mentioned before, we want to afford as much as flexibility as possible. What I mean by that is an end user can use a GUI like this, just select the channels that they want and route the signal. But for some reason, if the end user has certain algorithms in mind which they want to do, which they want to implement, we afford the possibility of doing your own coding and configuring the system as per your desires, your algorithms, etc. as well. So we want to cater to as many users as possible in that sense. Right. So a bit more detail about the electronic systems in itself, because this is something which at the moment we are moving from discrete units to making our own designs to make it very compact. The part we start off with is the driving array. This, as you know, is to drive any sort of phase shifter, so the gated mechanism within the photonic chip. And then the output from the chip is fed into a monitor system, which is then fed into a processing unit to complete the entire feedback loop. The processing unit is where we have our backends running as well. So at the moment, we were using a PC for this, and then we are moving into using a processor to have this as close to the chip as possible, and then make it into a small, compact subsystem, which helps out a lot, especially if you're planning on using this in a larger system in itself. Again, coming back to the software once more. So one of the features which we are adding in here is the lower level layer, which I mentioned before. This has basic routines, etc., which will be hidden for the end user. So this is basically the backend, but this also enables a custom coding platform for every end user as per desire. This adds a degree of freedom, which is not compulsory, but is an option for the end user depending on their requirements. The high-level system is something which I would assume most users would be interested in. This in itself has pre-characterization of the FPGA. It has added functionality such as configurations, auto-routing, and user-defined configurations as well. So one of the possibilities, which I have a slide on later on, is also uploading your own custom mask and asking the system in itself to basically fabricate or actually design a path which then can replicate that custom mask that you require. So custom transfer function in that case. And we also provide within this configuration part a monitoring system whereby you can assure that even within certain limits of temperature drifts, or within certain limits of temperature drifts in the photonic integrated circuit, you still maintain the performance as per desire. So moving on to some of the results and measurements that we have done, what we have already demonstrated is for the control of the circuit, we are using some advanced machine learning algorithms. I won't go into the specific details of them, but if you have any questions, please feel free to ask. What then happens in the back end and what we have demonstrated to date is, for example, beam splitter, the one example you have over here. This was for a 1/8 beam splitter, whereby you started off at the initial condition of the chip. What I mean by the initial condition is that you have phase errors coming off across because of the fabrication variances of each part of the circuit in itself. And then we have this automated mechanism to configure the chip so that you end up with a 1/8 beam splitter. As you can see over here, we have used several cost functions to optimize this as well. Excuse me. And then based on the cost function that you use, you require a set number of iterations to configure the chip, whereby after, in this case, it's 20 iterations, you will see that your performance is what you desire to be. We have done this for ring resonators for different filters like Mach Zehnder-based ones as well. And what we have done as well is a comparison of the dynamic performance of such configurations. What I mean by that is switching from one form of a filter across one particular path to another filter across a different path. Sorry. And we have compared these results with the static performance. This was also done to ensure that we do not lose anything when you reconfigure. So move from a static environment to a dynamic environment. Unfortunately, I cannot present a video over here, so I won't go into the details of that, but please feel free to ask about that if you're interested. Another feature which we personally are very proud of, which to me is very, very interesting, is that you can upload your own mask. This is what we call as the mask. So basically, if you need a certain filter with set parameters, you know how the filter should look like. You can basically just upload this into the system, into the program in itself, and then you will see that your control system based on the operations of the processing unit will configure and give you the desired filter performance that you need. So this is a very interesting feature. It gives an added degree of flexibility to the whole concept as well, which we are developing further and trying to integrate it into the entire system. In regards to the progress that we have made till now, as I mentioned, the concept, we have started working on it around 2015 with publications coming across around 2016-17 landmark. From the university end, we are working on an ERC grant. We did the FPGA concept and patents on that. We have moved on to improving the performance, improving the software and the and the control layer associated with this as well. A lot of the work also is on machine learning algorithms for self-configuration. And at the moment, we have new projects coming off, as you can see over here. There are a list of a few of them that we are working on, and we are trying to come up with the first prototype, which would be somewhere next year. So to conclude the whole talk, in regards to FPGAs or programmable circuits on a whole, there is a lot of scope. There's a lot of interest in this because it fills a gap which aspects themselves cannot provide for. There is improvements that still need to be done. So we are trying to tackle it in different fronts through different projects, different ideas, be that in the control layer, be that in the software department, be that in the physical design of the chips as well. And as I mentioned before, we expect to have a product on this, or at least the first prototype, beta prototype of this somewhere around next year. So hopefully we can get some, we already have some interest on this for testers, for people who want to give this a try. And we already are hosting some custom workshops to promote this further, to make available to the end user the ways of managing the software and how to drive it, etc., so that they're familiar with the software and the interfaces, etc. And my colleagues have also recently had a book coming out on this, so please feel free to read about it. This is a very complete book in the sense that it covers from the fabrication, from the big design side to the system level side of the whole programmable photonics concept. So yeah, if you're interested in this, please feel free to have a look. Thank you for your time, and if you have any questions.
Thank you very much, Prometheus. We we don't have any questions on the chat. Maybe one. So we can see that it's probably still a research tool and thrust that you're working on. Do you see emerging applications for it in terms of what kind of, if you look at the photonics community, do you see people that specify some potential applications when things will be mature enough in terms of?
Yes, that's a good question. So to start off with this, sorry, maybe you can mute your microphone once more. I'm getting a lot of feedback. Yeah, thank you. So firstly, I do want to stress on one thing that from our side, we want to be application agnostic in the sense we want to make it as generic as possible. But the most interest we have, based on the feedback we have had from people we have been interacting with, have been, for example, from people working in data centers, from people working on beamformers, on RF filtering. We have people working on neuromorphic computing, for example, showing a lot of interest, quantum computing as well. So these are fields we are looking into. What we also try to do from our side is interact with them and try to incorporate some, especially in the software side, some custom requirements that a particular field might have, which is a very nice thing to do, because if you have a generic hardware which you can customize from the software end, that adds a lot of value to the whole product as well.